Hey there, we're in the drone lab today. I wanted to talk a little bit about co-registration of drone products. A lot of work that we do here in the drone lab involves looking at change over time. And one of the biggest challenges that we have with that kind of work with drone data is getting imagery from multiple dates or different sensors to align, or in other words, to get it co-registered. Now, co-registration is a relatively straightforward process if you have some ground control points or if you have some recognizable and unmoving objects in your scenes. But we work in natural systems a lot, and that's rarely the case for us. A lot of the places that we work are actively managed forests or rangelands or industrial sites, and installing permanent ground control points that we can use over repeated time is just not really possible. So we need some strategies for how to co-register our drone data from different dates that uses only temporary ground control points or doesn't need any ground control points at all. And so in this video, we're going to look at using NOAA's online positioning user service, or OPUS, to post-process some local GNSS data to get better positioning and ultimately to let us co-register some map products in a very accurate way. Now, first, a disclaimer, I'm not a surveyor. I do have a decent amount of field experience working with drone data and GNSS systems. And we're going to look at sort of the empirical results of how well does this actually work for co-registering drone data.
First, let's try to get some understanding of what OPUS is trying to do and consider some different use cases for it with drone mapping. At a very simple level, OPUS is trying to improve the accuracy of a location estimate that has been made from a series of GNSS measurements. For example, if you put a GNSS receiver out at an arbitrary fixed spot and have it average all its location measurements for an hour, you can get a pretty good estimate of its location. Now, how good is pretty good? Well, generally you'll be within a meter of its true location, though the elevation estimate may be less accurate than that. Now, is that good enough for drone work? Well, it depends. If that GNSS receiver is your RTK base station and you just need a measurement from that one time period, it's probably fine. Your rover measurements may be offset by the amount that the base station is off from its true location, but they will be accurate relative to the base station, and measures of things like stockpile volumes or canopy heights won't be compromised. If, though, you need your drone map products to line up with other spatial data, or you want to look at change over time, then you need to have a high degree of absolute accuracy, meaning you need your base station location estimate to be as accurate as possible too. And that's what OPUS does for you. By submitting your base station log files to OPUS, it can use the network of available reference stations to correct or post-process the location estimates in your base station log files, giving you a much more accurate estimate of the true location of your base station. Okay, how accurate is accurate? Well, with OPUS, you can generally get within a couple of centimeters, which is usually good enough for most applications. It's worth noting here that there are other similar free services besides OPUS. Two of the main ones that I'm familiar with are the Australian version, OPUS, and the Canadian version, which is CSRS PPP. And while OPUS can technically be used outside the US, it mostly uses the US National Spatial Reference System sites, whereas the other services will use stations from the International GNSS Service Network. Also, OPUS at present uses only the GPS satellite constellation, though there's a new version in public beta that will allow you to use the other satellite systems as well. These other services will use GPS plus all of the other GNSS satellite constellations. Now, sometimes I've had a log file that won't process with OPUS for one reason or another. We'll talk a little bit more about that in a second, but I usually can get a good solution for these log files with another service like CSRS PPP, so that's just something to keep in mind. Now, there are three main steps that we need to work through to get our base station corrections from OPUS or a similar service. First, we need to pull the log files from the base station and prep them for OPUS. Now, every base station manufacturer is going to have a different procedure for how to do this. We use an MLID Reach RS3 unit for our RTK base station, and I pull those files directly from the unit. And I usually like to use MLID Studio to trim a few minutes from the beginning and end of those log files to get rid of any bad data or data that might be associated with like jostling the unit as we're getting it set up. OPUS won't accept log files greater than 100 megabytes. So if your log file is really long, you might want to decrease the sampling rate to every few seconds, or you can also exclude the satellite systems that aren't part of the US GPS satellite network. Also, worth noting, OPUS does not like special characters in file names, so make sure you strip those out before you go to upload your files. Okay, next step, we send the base station file to OPUS and get the corrections. This is pretty straightforward. You submit your trimmed log file via the OPUS website, and when it's done, they email you the solution back. OPUS has two versions. Static is for log files that are longer than 2 hours, and rapid static is for log files between 15 minutes and 2 hours long. It's worth reading about the accuracy that you can expect from each of these as a function of the duration of the log file, but rapid static is more prone to failing and not giving you a solution. And when that happens, I've always been able to get a solution using one of the other services like CSRS PPP, but for that reason, we generally try to leave our base station up and running for at least 2 hours so we can get a log file long enough to run through OPUS static. Okay, third step, once you have your solution from OPUS, you can use that location as the true base station coordinate values when you post-process your rover data or your logs from your RTK drone, or you post-process sensor data from, say, like a lidar unit. Now, if you compare the OPUS corrected versus the uncorrected points, like in the example of ground control point locations measured with our IMLID reach system, you'll notice that the points are just offset by the same amount. And that makes sense, right? Because OPUS just corrected the base station location, and then we used that to adjust everything else based off the improved location estimate of the base station. To look at how OPUS works and the effect that OPUS corrections can have on co-registering drone data, let's look at a real scenario. We've got some drone data from a site where we fly to get volume estimates on a monthly basis. And we collect drone imagery at the site in a double grid pattern, and we have 9 ground control points that we put out and measure with our IMLID GNSS system, which again is the Reach RS3 as the base station and an older Reach RS Plus for our rover unit. Now, this is a very active work site, and there aren't good places for us to set up permanent ground control or to even have a fixed location for the base station. Every time we've tried to set up a fixed base station location, we come back the next month and find they've driven a loader over it or something. So to get the best accuracy and to make sure that our map products are co-registered between months, we need to correct the estimated location of our base station from every time we go out. For this example, I've pulled up some imagery from 2 different months and gone ahead and processed it in Metashape to produce elevation models and orthomosaics. For both months, I processed the imagery twice, once for with and again without OPUS corrections. And this will let us see the effect that adding OPUS corrections to our workflow will have on, 1, the offset within a month in terms of the orthomosaic as well as the elevation model, and 2, the alignment between products from different months, again, for both the ortho and the DEM. If we start with the orthomosaic from the first month and toggle back and forth between the corrected and uncorrected versions, we can see that we've got quite a big offset. If we zoom into the location of the base station itself, we can see that the offset is actually about 2.7 meters in the X direction and 1.4 meters in the Y direction. That means that the base station location that our IMLID RS3 estimated for itself was about 3 meters off of its actual location as estimated by OPUS. Now let's take a look at the DEM next. All these DEMs that we're going to look at are on the same color ramp and scale, meaning that the differences in the colors between them indicates a difference in elevation. So looking at the DEM for the corrected and uncorrected versions for the first month, we can see there's a pretty big shift in elevation. Big as in like almost 5 meters big. But again, if we just want to estimate volume for one point in time, this doesn't really matter because we're going to draw our polygons sort of based on the data product that we have. And so we'd get the same estimate despite the offset. Now, where things start to get interesting is if we look at the difference between months. If we have no OPUS corrections, there's quite a large offset between the corrected and the uncorrected versions, with the difference being about 1.7 meters in the X direction and about 70 centimeters in the Y direction. Honestly, this is actually better than I thought it would be. This would, of course, cause some problems if we're trying to measure change between time. Now, as an aside, I'm not exactly sure why we'd want to measure change like this for this project site. This is something we typically do in other cases, like measuring change on a stream channel. But this site just provides a nice and clean sort of example of what's going on here. Now, if we look at the DEMs for the uncorrected versions, we can also see that they're way off. If I do a quick DEM difference, just subtracting the cell values of one DEM from the other, it'll highlight the areas that have changed. But the areas that have not changed, like the asphalt pad here, should have a value of 0. But with the uncorrected versions, we see that the difference is on the order of a whopping 6.5 meters. And we can't just add that amount to the difference, though, because of the X and Y offset, which causes the DEMs to not line up well with each other. Now, let's look at the OPUS corrected versions for both months. From the orthos, we can see that the months are pretty well lined up with each other. Any difference is on the order of a centimeter or so. The DEMs also look really well aligned vertically, except for the piles, which of course are different. If we redo the DEM difference, we can see that in the areas that haven't changed, the difference is pretty much on the order of a couple centimeters, which is about the best we could expect with the current setup we have. Okay, so what are the take-home messages from this example? First, it's pretty clear that the OPUS corrections for your base station locations will help tremendously for co-registering drone data over time, even if your base station is set up at an arbitrary point. Second, I'd say from experience that you never know when you might need to do some time series comparisons in the future, or you may need to co-register your drone data with other data sets. So you probably should just go ahead and do the OPUS corrections anyway.
Okay, that's it. Hopefully you found this video useful. OPUS or another service like it is a really great option for getting the best accuracy out of your drone products. At the Drone Lab, we now do OPUS corrections anytime we put up a GNSS base station to collect ground control points, or in our RTK or PPK applications like post-processing lidar data. For change detection projects, though, this technique requires GNSS data from both dates in order to work, which is not something that we always have. So in a subsequent video, we'll look at a co-registration technique called anchor images that can work in a lot of situations where you either have ground control data from only one date, or you don't have any ground control information at all. Thanks for watching.